In this video, we will be going over amine nomenclature from my notes, and then we'll do a whole bunch of practice problems. So, naming amines. Amines can be alkyl or aryl substituted, which makes alkyl or aryl amines. So, alkyl means a carbon chain, aryl means a ring structure substituent. And amines are classified as primary, secondary, or tertiary, and we use these terms to mean how substituted N is in an amine rather than how substituted carbon is like we do in other compounds. So notice here that tert butyl amine is a primary amine because it is only substituted once. And this is not a new idea. We've been doing this with carbon for 23 chapters. A nitrogen can also form four bonds, and that's called an ammonium salt. You'll never see those. Primary, secondary, and tertiary amines are named pretty much the same way on how many organic groups are on the nitrogen. So for simple primary amines, add amine to the end of the group, and you'll find your parent alkyl group, and then name it. So tert-butyl amine, like we already looked, primary, and you've got a tert-butyl attached to it. Cyclohexyl, of course, you got your cyclohexane, and then aniline. This is a common name. You'll have a bunch of compounds with common names. That's nothing new, and you'll get to learn them as you use them over and over again. So notice here the alkyl subgroup, and you find the alkyl subgroup, and then the amine is added to the end. So following suit, you replace the E of an alkyl chain with amine of the parent compound for more complex ones. So you have 4,4-dimethyl cyclohexane amine, because amine is a subgroup added to it. And here you have 1,4-butane diamine. So you would just name the parent chain 2, 3, 4, and you've got an amine on 1 and 4. So for amines with more than one subgroup, consider the amine just as a subgroup and they're named normally. So you have 2-amino-butanoic acid. Notice it changes to amino when you have multiple groups on an alkyl subchain. So it looks like the example here already named it for us. So we've got 1, 2, 3, 4, and that's amino-butanoic acid. You've got a butanoic acid here with an amino group on the second carbon. So 2,4-diamino-benzoic acid. Here you have a benzoic acid. And notice that these are named for the lowest locants. So 2,4-diamino, because there's two of them, benzoic acid. And then 4-amino-2-butanone, same thing. You number your carbons, you have butanone here, and an amino group on the fourth carbon. So secondary and tertiary amines that are symmetrical. You just add the prefix of the number of alkyl groups to the amine. So diphenylamine, you've got two phenols, attached to the nitrogen, diphenylamine. Here we have triethylamine, so nitrogen is your central atom, just like you normally do with carbon as your central atom. And you've got 1, 2, 3 ethyl groups, triethylamine. Unsymmetrical ones, if they're secondary or tertiary, you name the biggest alkyl group as the parent name, and anything else attached to that nitrogen you name as N comma or N hyphen with the group. So our first example here is NN dimethyl propylamine. So you have NN is what's attached to the nitrogen. So NN tells you that there's two methyl groups attached to the nitrogen. Boop boop. And then you have a propyl group. Bam. So NN dimethyl propylamine as your parent chain. Here your biggest alkyl group is your cyclohexylamine. Boop. And then the N-ethyl N-methyl tells you what's attached to the nitrogen. N-ethyl N-methyl. Oh, I did that backwards. So heterocyclic amines. A ring with an N as part of the ring makes it a heterocyclic amine. That nitrogen is always numbered as number 1, and different rings have different common names. So you can look at the systematic name if you want to look fancy schmancy, and you add the prefix aza for each nitrogen, and then di, tri, etc. And I included both tables here. So you of course consider that nitrogen as number 1 using the systematic naming, and then you name the rest like normal. So we'll look at these, but they get tough to name if you use systematic because you have to name the double bonds as well. And then you need to name the double bonds and everything else as part of the ring structure. So we'll just use this group right here. So here's some of the common names. And in the second chart, the second chart also has the systematic name. And I circled pyrimidines and purines, which should ring a bell from your bio classes. Those are your nucleotide bases. And now let's look at some examples. Problems in practice. So scrolling up, name the following compounds you're going to have in point one. These are just the in-text problems from one of my textbooks. So for 24.1, those are the examples, and those are showing the molecule you have to name. 24.2 and 3, you have to draw the structures. In point 2, we're doing linear. Point 3, we're going heterocyclic. So for A, name this one N-methyl ethylamine. So I think of these the way that I drew it out underneath the print. Everyone has different ways of drawing them, but it makes sense to me to draw the bonds with nitrogen in the middle, like the in-text examples. It just makes, I can just picture and name it easier that way. Whatever works for you. So here you have an ethylamine, and that's your parent chain right here. And then you have a methyl attached to the end. Oh, and keep in mind that for primary, secondary, tertiary amines, you add amine to the parent chain, remove the E. If it's symmetrical, use di, tri, etc. And if it's a big unsymmetrical one, use the large alkyl group. So for B, we have a symmetrical one, and that has 3 cyclohexenes. 3 is tri, so tricyclohexylamine. And you might see it drawn with the cyclos in parentheses like this, which is okay if you want to do that, whatever works for you. And C, remember, if it's unsymmetrical, you use the largest subgroup as the parent chain. So the parent chain here is cyclohexene, which is a 6-carbon ring structure. Since it's tri-substituted, you know you have 2 names attached to the end. So you break it down as you go. You have your methyl cyclohexylamine as your parent chain, which I labeled here, and then you have a double N, so just break it down as you go. N-ethyl, N-methyl. So that's what's attached to the nitrogen here, ethyl-methyl. Now for D. So do you remember this guy from the outline earlier? It's one of those common names. So since the subgroup is methyl and attached to the N, you name it N-methylpyrrolidine. So if you want to be fancy-smancy, you could call it methyl azacyclopentane or something like that, but we'll keep it simple and just stick to the most simple name nomenclature for this. And E. If you have a symmetric one, this one is symmetric and it's shown a little funny to throw you off, so you just break it down. Find your N and go from there. So identify the subgroups attached to it, add the number prefix, and end with amine. So here you have a nitrogen. There's 2 isopropyl groups attached to it that I circled in purple. And this one is di-isopropyl amine, because there's 2 isopropyl groups attached to the amino. So I drew it with the carbons and hydrogens on there. That helps me figure out the naming in my brain. Whatever works for you, go ahead and draw it that way. And F, this one's pretty tricky. You have 2 nitrogens, so you know it's a diamine, and nitrogen is not the central atom. So you name the longest parent chain, which is butane. MEPB, B for butane, MEPI. 1,3 butane diamine. You have to name from the carbon on the left as carbon 1, so that you get your amino groups as 1 and 3. If you name from the right, you end up with 2, 4, and we can't have that, can we? So for point 2, we're using the IOPAC names for some straight chains. Triisopropylamine for A, and you can write out the formula. I like to draw the molecule. I use the sticks instead of writing out C's and H's if it's bigger ones like this. And this is a tertiary nitrogen. So triisopropyl, you draw 3 isopropyls attached to a nitrogen. For B, it's the same as A, and allele group is a CH2 double bond CH-CH2. And I had to look that one up. It's the same as A, so just add 3 of them. I drew out the stick version and the formula. It looks like I drew the sticks right. If you want to draw formulas, feel free. So that's triallylamine. Now C is N-methylaniline, and aniline is a benzene ring with a nitrogen on it, not in it. And the nitrogen methyl tells you that methyl is attached to the nitrogen. So that's methylaniline, N-methylaniline. And for the rest of them, for D, we have N-ethyl, N-methyl cyclopentylamine. And the way I drew it, this is not a synthesis, it's just how I draw these. So you draw the parent chain first, and that's cyclopentylamine, which is the parent chain. And then the N-eth and N-methyl tell you that both groups are attached to the nitrogen. So draw the parent chain, and then attach them to the nitrogen. N-ethyl, N-methyl cyclopentylamine. So for E, again, it's not a synthesis. I'm just showing my logic. So you have the parent chain, and then you add the stuff that the name says is attached to the nitrogen. And then I finished up by adding the nitrogen because nitrogen needs 3 bonds to feel secure in itself. So we have N-isopropyl cyclohexylamine. So here you have the cyclohexylamine, isopropyl, 3 bonds. For F, so I drew the pyrrole and add the ethyl. I drew it 2 ways here. So you could also write the formula. I can't intuit structure for formula too easily, so I just draw the molecule. And F is the N-ethyl pyrrole. So I drew the pyrrole and then N-ethyl. So you just add the ethyl group to the nitrogen. Now, getting into the heterocycles. Heterocycles are the worst. It's an indole. In this, for A, it's an indole ring, and you don't count the carbon that the arrow is pointing to as a carbon. So be really careful when you're naming these that you get the numbers right for the heterocycles, because they don't all name the same. They don't all number the same. The technique for naming doesn't change though. You take the parent chain and add the subgroup to the correctly numbered carbon. So for 5-methoxy-indole, you take an indole and you just add a methoxy group to the 5th carbon. So I drew one out here, but it's kind of ugly, so I used the picture from the table, and that's how you draw that one. For B, we have 1,3-dimethyl-pyrrole. And my drawing's terribly ugly, forgive me. So you draw the pyrrole and then add the methyls in the spot that give the lowest locants. And you should know how to do this by now. You can sort of intuit which gives the lowest locants. For some of them, not all of them. So that's how you draw 1,3-dimethylpyrrole, since N is you count N as the number 1 position. So for C, 4-NN-diethyl aminopyridine. You draw the parent, and there's your aminopyridine. And then add the subgroups and name for the lowest locants. So the NN tells you both methyls are on the N subgroup on the 4th carbon. So be careful when you attach these methyls in this particular problem, since you're not attaching it to the nitrogen in the ring. You're attaching it to the nitrogen on the 4th carbon. So that's why it's in parentheses, the 4-NN-diethylamino. So I added a pic of the pyridine, so you don't need to go back and look at the silly chart. And so just be really careful when you're naming those to number it correctly, and that you don't add it to the N on the nitrogen if it's 4-NN. Now for D, why is this 5-aminopyridine and not 3? And that's because of the way it's numbered. Because of the way pyrimidine is numbered, you go from nitrogen to nitrogen on this one, and that becomes important when you start to look at nucleotides and nucleotide derivatives. I'm not sure if you'll be naming those for your organic class, but some do. So that's how you would do 5-aminopyrimidine. You take the pyrimidine, add the amino to the 5th position. And that ends the video. Thanks for watching.